Okay, so for 2.1, it's a pretty short section. We're gonna talk about tangent and velocity problems. So one of the main things you focus on in Calc 1 is the instantaneous rate of change. We also then will talk about integration at the end of the semester, but in the beginning, we really want to focus on the instantaneous rate of change and kind of how it comes from the average rate of change and how we can develop that concept to come to be in instantaneous rate of change. So let's take a look at an example first to kind of see what we're getting ourselves into. It says the position S of t of a ball in feet at 1 second time intervals is given by the chart below. What is the average velocity of the ball over the time interval 2 to 5? So basically we have this chart of data, and we have t equals 1, 2, 3, 4, and 5 seconds. And then we have s of t, which is the position function. Oftentimes in this class, I'm going to use s of t to represent position. V of t would be velocity. And normally in this class, when we say v of t, we mean instantaneous velocity. And then a of t would be acceleration. So we have these values, and we want to find the average velocity. So what I'm going to do is I'm just going to write v average. Okay, and you guys know that the velocity is the change in distance or distance over time. But if we're going to find the average, then we're going to find the change in distance over the change in time. And this is how we can find our average velocity over this interval. So all we're going to do is we're going to just say that v average, and again, just get comfortable using subscripts a lot. It's a very important little notation tool in calculus. It allows people to talk about variables, and the subscript kind of tells you what you're saying about the variable. So in this case, we're talking about the average velocity. So v average is worth, well, to find the change in distance, won't I just do s of 5 minus s of 2 divided by 5 minus 2, right? So s of 5, we see s of 5 is right here, is 55. So I'm going to say 55 minus s of 2. We see s of 2 is 12. So I'm going to say 55 minus 12 divided by 3. So then this will be what, 43 over 3? And that would be our average velocity, okay? So we can then take a look and see what we just did, okay? So if I just give you like a rough sketch of what we're getting ourselves into here with this graph, and again, this is just a rough sketch. Let's say that the graph looks something like that, okay? And then what we did is we found, let's say that this is at, I don't know, 1, 2, 3, 4, 5. So here's 2 and here's 5. So what we did is we found our height right here, and we found our height right here. And then we found the average of that, okay? So this is technically 2 points, and we found a secant line. Oops, that's a really bad secant line. Right? And as it turns out, this 43 over 3 is the slope of the secant line. Now think back to when you learned slope, right? Slope was the, you learned it as rise over run, but wasn't it the change in y's divided by the change in x's? Right, your old school formula for slope was y2 minus y1 divided by x2 minus x1, right? Well, literally what I did with v average is I found the height of the position at 5 seconds and the height of the position at, or I should say the position at 2 seconds. So I literally found 2 y values. So when I said this, I said s of 5 minus s of 2. And then I said my x values, well, this is t, right? So then I said 5 minus 2. So literally what I'm doing is I am doing the slope formula. So your old school formula that you learned for slope all those years ago is still coming back in Calc 1. And what'll make it graduate from pre-calc or algebra to calculus is when we start talking about instantaneous rate of change, okay? Or the slope of the tangent line. So that's what's actually happening there, okay? So let's kind of summarize here and get a little formula for us. So we have the average rate of change of a function on the interval a to b is given by the formula f of b minus f of a all over b minus a. And this is the slope of the secant line. So we have the slope of the secant line, okay? So what we could do is, what if we took our graph, oops, and let's take a graph similar, let's take a graph similar to the one before. And I'm just gonna draw, you know, some shape like this. Oops, it's a little, I want it a little steeper than that. Okay. And let's say that this is A and this is B, right? So this distance from here to here, let's call that distance from A to B, let's call that H. You know, let's just say that it's some distance called H. So I have my secant line. If I were to do this again, I'd have my secant line right here, right? So that is the secant line. So if I found the slope of that secant line, would you guys say that it's a good representative of the graph right here? Probably not, right? I mean, at least they're both going in the positive direction, but I don't feel like it's a very good representative. So what I would do is I would try another graph. And I would pick up B, and let's say I move B a little bit closer. Let's say I put B right here, okay? So now, you know what, let's call it C, I guess. Let's say I pick it up and I put it right there. So now if I draw my secant line, oops. Now if I draw my secant line, it's a little bit better. Now would you say that the slope of that secant line is a little bit closer to the slope at A, right? But it's still not perfect. So what if I picked it up and I put it like right here, and let's call that D, okay? So now I'm gonna put my secant line right there. And now I'm gonna have that. So now A and D, when you draw a secant line between them, is starting to become closer and closer to the true slope of the line at that moment of A. Now, the thing is, how close to A can we get? How far can we keep picking up this point D or E or F and moving it closer and closer to A? Well, we can get infinitely close, right? We can get so close that you can no longer tell the difference. When you start approaching that idea of infinitely close, you're starting to see the idea of limits. And that's when we can find the slope of the tangent line. So notice a tangent line only touches a graph one time. So what we're working towards is we're saying, okay, we can find average velocity by using a secant line and then finding that slope. And remember, slope is just the rate of change, right? But if we want to be instantaneous, then we need to have a slope, you know, at that moment in time, at A, you know. So in order to do that, we're going to have to work our way through eventually, which will be derivatives. But the first concept will be limits, and this idea of getting closer and closer, but never actually making it to the value. Okay, so what happens is we keep picking up this point and moving it closer and closer and closer and closer to A until we can no longer tell the difference between our point and A. And then when we try to draw a secant line, it becomes a tangent line. Okay. And again, we can only do so good with drawings because, you know, they're human made. We're talking about a concept of infinitely close that only exists in our mind, right? So let's take a look at an actual, you know, a problem that you may see in the homework. Okay, so it says, find the instantaneous rate of change of, and then I'm going to give you y equals x squared plus 2 at x equals 1. Okay. So basically, I haven't told you guys how to find this per se. All I've shown you how to do is how to find the average rate of change. And if we want the average rate of change to start approaching the instantaneous rate of change, we have to keep moving our value closer and closer and closer to the point. So what I'm going to do is I'm going to draw a little chart and I'm going to put some intervals. Okay. So I'm going to have intervals. Okay. And then I'm going to have average rate of change. And then I'm going to have, no, that'll be it for now. So my interval will be from 1 to 2. So when we first do our secant line, we're going to just choose the point 1 and choose the point 2. But then we're going to pick up our point and move it closer, and we're going to say 1 and 1.5. And then we're going to pick up our point and move it closer, and we're going to say 1 and 1.1. And then we're going to pick up our point and move it even closer and say 1 and 1.01. So what we're doing is we're just continually moving our point, just like I did in here. I'm just picking up my B and moving it closer and closer to A. Okay, so what we're going to do, so what we need to do is we need to do some calculations. So we're going to find the average rate of change. So we know that V average, we'll do it for a few. So what I'd like you guys to do after I do this first one is pause the video and fill this table in. So we're going to do V average for the first guy. And the first guy is going to be f of 2 minus f of 1 all over 2 minus 1. So what I do is I'm now going to take 2 and plug it into here. So that would be 4 plus 2, which is 6, minus plug 1 in there, which would be 1 plus 2, which would be 3. And then we're going to divide it by 1. So we get 3. So then right here, I now have my average rate of change is 3. Now I need to do that again for each one of these. So pause the video and give these 3 a shot, okay? All right, so hopefully after you guys have unpaused the video, you ended up getting 2.5 for this one, and 2.1 for this one, and 2.01 for this one. And all I did was the same thing you guys did. I did V average again, and this time I did f of 1.5 minus f of 1, all divided by 1.5 minus 1, which should give you 2.5. Okay, so we're literally doing what I did right here. We're picking up the value of of B, of C, and of D, and we're moving it closer and closer to A. Okay, so now I went from 3 to 2.5. Now I go closer and I get from 2.5 to 2.1. I go even closer and I get 2.01. So what this is telling me is, I believe the instantaneous rate of change is approaching what number? Again, I haven't made it to this number, but I think it's approaching 2. So that's what I'm going to say my answer is. I feel that the instantaneous rate of change is going to be 2. Now, again, all I did was find the average rate of change from one side, okay? So what I should do is I should go from the other side then. So I'm going to do an interval this time, but from the other side. So I'm going to go from 0 to 1. I'm going to go from 0.5 to 1. I'm going to go from 0.9 to 1, and I'm going to go from 0.99 to 1. So all I'm doing is coming from the other side of 1 this time, and this is going to become the average rate of change. Okay, so I'm going to do the same thing. I'm going to do f of B minus f of A. So this would become V average equals f of 1 minus f of 0 all over 1 minus 0. And we know that when we plug 1 into this formula, x squared plus 2, we're going to get 3 minus, what would it be, 1 over 1. So we should get 2, I believe. Oh, no. I think it's 3. Is it x squared plus 1? It's x squared plus 2. Sorry about that. So it's 3 minus 2 over 1, which is 1. So we're going to get 1 right here. So now you guys should pause the video and do this again for the following ones. And there's quite a few homework problems that ask you to do this as well. So you get practice. And then when you plug this one in, you should get 1.5 now that you're back. And then 1.9 here, and then 1.99. So coming from the left side of 1, what does it look like I'm approaching? It looks like I'm still approaching 2. Coming from the right side of 1, it looks like I'm approaching 2. So I'm very confident now that I feel like the instantaneous rate of change or the slope of this graph at 1 is probably 2. Okay, now again, we didn't definitively show it because we never actually made it to 2, but I feel like I'm 2.01. What's the next value going to be? 2.001 and 2.0000001. And then here it's going to be 1.99, 1.9999999. So I feel like we're approaching the value of 2. We'll never make it with the table. We won't actually make it to 2 with the table, but that's where we're going to make this leap, and we're going to say, okay, but if we had an infinite amount of time, or we could approach an infinite amount of time, I could make it to 2 if I could just keep taking cuts and getting closer and closer. Okay, so let's do this in summary. Oh, and if we wanted, could I find the equation of the tangent line? Well, what do you guys need to find the equation of a line? Don't you need? We need a point and a slope. Well, we have the slope. We just found it. We said that the instantaneous rate of change is approaching 2. This is math code for slope of the tangent line. Okay, so we know the slope of the tangent line is 2. We also know a point on the graph. We could just plug 1 in. If we plug 1 into here, we plug 1 in, we get 3. So we know there's a point on the graph of 1, 3. So what I'm going to do is I'm just going to write my formula for finding the equation of a line. I use point slope form. So I'm just going to use y minus y1 equals m times x minus x1. But you guys know that this is y minus, now y1, we're using, remember, we're using the point 1, 3, right? Because I plugged it into the original function and it spit out a value of 3. So it'd be y minus 3 equals my slope of 2 times x minus 1. So here is my equation of my tangent line. And you could put it in y equals mx plus b, but I didn't ask you to. So this is our equation of our tangent line. So we can also find that. So let's kind of summarize. So average rate of change equals the slope of the secant line. And we know that this formula, m equals f of b minus f of a all over b minus a, is equivalent to our old school formula for slope. And this is how we can find the slope of the secant line. And we know that instantaneous rate of change equals the slope of the tangent line. Okay. And we can find this. We can find this by making secant lines closer and closer to the given. Okay, now that's not perfect. We're not there yet, but this is how we've decided that we can do it this way by picking values closer and closer and finding secant lines closer and closer. We're going to be able to estimate at this point instantaneous rate of change. Okay, so let me have you guys try a few of these. Let's see here. So this one, I'd like you to find the average rate of change for y equals 3 minus 2x squared on the interval 2 to 2.4. Okay. And then follow that up with find the instantaneous rate of change to f of x equals x cubed at x equals 2. Okay. So pause the video and give these two a shot, and then when we come back, we'll kind of work these out together. All right, so hopefully you guys figured out to find the average rate of change. It's no big deal. We're just going to say m average, right, is equal to 3 minus 2 times 2.4 squared minus 3 minus 2 times 2 squared, all divided by 2.4 minus 2. So let me just take out my calculator. So I'm going to do 3 minus 2 times 2.4 squared minus 3, oops, let me put parentheses, 3 minus 2 times 4. Divided by 2. So you should get negative 8.8. Hopefully that's correct. Oops, let me write it down here. Negative 8.8. Okay. So it appears that I'm running out of battery, guys. So I'm going to have to go get my charger, but I think I'm just going to end the video. So the slope of the tangent line, this would be 3x squared. So the slope of the tangent line, I believe the answer for this one should be 12. Or instantaneous rate of change. Let's see, 3x squared times 2 would be 4. 4 times 3 would be 12. So that should be 12, but give it a shot, try to do it. What you're gonna have to do is you're gonna have to build intervals, right? And then you're gonna have to find average rate of change. And you know, a good interval to use, if you're going from 2, you can use 1 to 2. We can go from the left side, and then we can go 1.5 to 2, and then we can go 1.9 to 2, and then we can go 1.99 to 2. And then you should do it from the other side as well, but because this is a polynomial, you guys will kind of see with polynomials, whatever's coming from the left, it's going to be the same from the right. And then you should be able to go from there. But I'm going to end this first video, guys. Thanks for watching. See you in class.